Okay, welcome to EE123, Lecture 4. Woo! The thing is, I need it. Because it's too early. It's just getting here, like, on time. Anyway. I'm talking now. It's my turn. You're more than welcome to participate in class, though. Okay. Are you ready? Are you ready? No? No? You should be ready. It's exciting. We're learning tools, things to analyze things. Okay, last time. Amazing tool called a DTFT, Chapter 2 in the book. Please go over it. Today, we're going to finish the DTFT today. Then briefly going to talk about the Z-transform that a lot of people actually are having a hard time with. So you got to refresh your memory on the Z-transform. We're going to cover it a little bit. Read Chapter 3 in the book. Now don't forget, Ham lecture class is today 6:30 at 521 Corey. Anybody planning to come? Oh, great. Fantastic. Yeah, I'm going to put slides on the B courses for 188. I'll create one for that class.
Can you get a unit for it if we can't show up to the lecture, but take the
If you take the exam, yeah, absolutely. What was my point? Yes, DSP. We're going to start. Ooh, okay. So quick question. Some people in previous year complained that I don't write on the board too much. And I use the slides. Now, that is because they haven't seen me write on the board. So they complain. But if I go too fast on things, please slow me down, and I can go a little bit slower. Slides do tend out to be faster. So please go ahead and say something if I do go too fast. And I'll try to bear with you. But it's just, I think for all of us, it's going to be more efficient and more useful if we use this. Something that you can actually read. Okay. Any questions before we start? No? Nothing? How's the discussion? It's good? Yeah? John complained you guys are not interactive. So can you do me a favor? Just for the sake of getting the TAs entertained? You'll see it's going to work much better. It's going to work much better. Okay, I just want to show you something fun that I've just seen recently. The what? Damn it. Okay, all right. Okay. Actually, I need to change it to $2. And your name? Lucas. Lucas? Like this? $2. Ah, boy, I made it today. That's why. You should be like on top of those because that's. What? Nah, I'm gonna change it. Okay, I should fix it. Oh, you're just wasting time. Something. Okay, you really don't want to talk about the Z-transform today, huh? Okay. Okay, so this Gotenna is just a product that I've seen, and what it does really, it's kind of like a text messaging for radio. So if you don't have cell phone reception, in areas that you don't have cell phone reception, or the towers are just too busy, like in concerts and things like this, they created this device that connects to Bluetooth to your phone. It has a radio in it with a microprocessor that sends basically packets. Which it allows you to do one-to-one communication. So your cell phones, just because of how FCC and how the cell phone industry is organized, your cell phone cannot actually communicate to each other. They have to communicate through a base station. So this device allows you to communicate over about 0.5 to 5 miles, depending on line of sight, to other people with the same device. It establishes this kind of ad hoc network. It operates on the MURS, which is a multi-use radio service. It's a unlicensed band on the VHF, and you'll know what a VHF actually means, but it's about 150 megahertz in that range. Maximum of 2 watts. Give you this kind of a range. And it does have encryption in it. So if you have an amateur radio license, you cannot encrypt anything because you use it just for a hobby, and it's self-policed. But on the MURS frequencies, you can do encryption, but you cannot transmit more than 2 watts. Trade-offs. It costs about, it's $100 per device, but you have to buy 2. Okay. As it turns out, the cool thing about it that I thought is that Lab 6 implement a similar approach. Basically, you're going to use your laptop and a radio to send text messages to each other. Okay, so it establishes something similar, only this one has a really slick system integration that a company can afford putting it together in a small device, with a nice battery and seamless operation. So I thought this was pretty cool. And the other thing that I just thought hilarious was, I'm going to show you the video. It's a promotional video, but just you got to watch the beginning, okay? And the reason you want to what they promote, okay?
Remember the last time you needed to send a message or tell someone where you were, but for some reason you couldn't? What a drag. That's because there were probably too many people.
So they're going to solve all these people's problem. Now, do you see the last person? He's trying to sell something privately, okay? And they have it on it, explicitly, which was just hilarious to me. If you see at the end, that's a solution.
It's time to start your own network and make no service, no problem. Go 10.
Wait. It was.
You send over Go 10.
Okay. It's just fun and hilarious.
Also, everything you send over Gotenna is completely private.
Right? Okay, look, I'm not promoting anything here, but this is on the website. That's pretty daring. Anybody want to work there? I don't know. Okay, I thought it was pretty sweet. I don't know. Anyway, so this is you'll know how to do this. This is actually, doing this. Okay? And the thing is, what I'm trying to tell you is, I'm going to show you all these examples to the class, but there's a lot of opportunities to come up with some ideas, related to processing signal, transmitting signals, doing all sorts of small devices right now, because everything becomes a little bit cleaner, cheaper. There's lots of small microprocessor, energy, more energy efficient. So there's a lot of room for innovation. And I'll show you a few things through the class. Okay. I wasted 8 minutes. Okay, so last time we talked about what did we talk about? DTFT, discrete time Fourier transform. That's a great transform. It is a fantastic transform. Now, we looked at a few examples, but now I want to talk about a concept which is called a frequency response. And we talked about different classes of DTFT. We talked about different classes of systems. One of the classes of systems that we talked about was the linear time invariant systems. And so now I want to ask you, we're going to talk about this very important concept, which is a frequency response of an LTI system. And what is really a frequency? There's a time response. Okay, that's pretty obvious. We talked about that. For example, an impulse response, LTI systems are characterized by an impulse response completely. If I know the impulse response, give me anything. Just give me something. I don't need to put it through the system. I know the impulse response. I know what's going to come out. Okay? I know what's going to come out. Very powerful. Another concept is the frequency response. But what is the frequency response of a system? Yeah?
That's the amount that a frequency gets scaled.
Wait. So frequency response is the response of the system to a pure frequency. All right? That's what it is. That's a frequency response. Time response is a response in time to a time signal. Frequency response is a response to a frequency. That's the concept. So you put a pure frequency in, okay? EEI omega 0 n. Okay? Oh my God, it should be J. I found it, $2. Okay, it's fine. Okay, you put a pure frequency in, you get something out. Now for linear time invariant system, z at the end, the output is going to be very particular. For nonlinear, non-time invariant system, the output can be like, I don't know. But for these type of system, the output is very interesting and known. So how do we find the frequency response of that system? This side. Not people that come to my group meeting. Yeah.
Take the DTFT of the impulse response.
Take the DTFT of the impulse response. Of that, another impulse response, of this. Take that. Let's compute the DTFT of this, right? Okay, that's great. So y of n, the output, is the convolution between this and the impulse response, right? Okay. Convolution between that input and the impulse response of that system. Great. Fantastic. Okay, so we want to compute this. So let's look inside and see what's in here. Okay, I look, and I was like, okay, summing over k's. Oh, wait a second, there's an n here. N is not summed over. We can take it out. So let's take that n out. Out. Over here. Okay? As if I've written it on the board. Out. And now we've just sums over k's. Now, if you stare at this long enough, like I do right now, at least from here, I see something very special happening here. Do you recognize this? Pattern recognition. Computer vision or human vision. Can you see what's going on? What is this? What is this? It's a DTFT of, but this is not a variable. This is a constant. Right? Double omega 0 is a constant. It's not a variable. So it's the DTFT of h of k evaluated at the frequency that we put in. Okay? So let's call it a name. Let's call it h e to j omega. Right? Evaluate it, omega equals omega 0. Okay? So that's pretty cool. And the cool thing about it is that h e to j omega is actually the DTFT of h of n. Okay? So y of n is the valuation of the DTFT of h of n at omega equals 0, multiplied by the original frequency. Fantastic. That is great. So for LTI systems, if I put a pure frequency in, I'm going to get the exact pure frequency out, except it's going to have maybe a different amplitude and phase shifted. Okay? So no new frequencies, no other things, just the same frequency in, only delayed maybe, so phase changes, or amplitude changes. And that depends on the DTFT of the impulse response. Okay? So the impulse response still characterizes everything. Now if you look at it closely and you took some linear algebra, you'd recognize that if you have an eigenvalue vector system, you have a matrix multiplied by a vector. You get lambda times v. That's the definition of an eigenvalue. When you have this property, that means that v are eigenvectors of that system A with eigenvalue lambda. Okay? So if you put a particular vector and that vector stays the same except that it's scaled, sounds similar? You put something in, signal in, it's only scaled or phase shifted, so multiplied by some constant. That's exactly an eigenfunction. And so e to the j omega 0 n are eigenfunctions of LTI systems. All LTI systems are composed of these functions. Okay, you put that function in, you're going to get that function out, only scaled. It's going to be very important when we talk about the DFT. We'll see what are eigenfunctions of the DTFT, of the DFT, and you'll see that they're very interesting. Okay? All right. Questions? So I'm about half a lecture off all the time. Like I finish my lectures in the middle, and then I start in the middle, and I end up in the middle. I'm either going to catch up or just delay them. And, that's kind of my questions. I put a pure frequency in an LTI system. What do I get out? Same thing. Okay? If that's what you learn, that's really important. Okay. Frequency response of a causal. So let's look at another example. Frequency response of a causal moving average filter. What's a moving average filter? Is exactly what it says. You take a window, you compute an average over that window, and then you move it. And then you compute. People use that term basically for computing average over kind of a sliding window. Okay? The definition of it is basically summing from over the last m samples. That's because it's causal. Okay? The past m samples till now, till the current sample. That's a moving average. And then divided by m plus 1 because we have m plus 1 entries. Okay? So what type of filter is this? Moving average. You talked already. Somewhere in the back. Yeah. A low pass. Why? Yeah, it smooths out stuff. Yeah, absolutely. 2 points. Okay, it is a low pass. And effectively, the impulse response looks like that. Okay? This is the impulse response. Okay? If you convolve this with some signal, you get this effective low pass. So now we want to see, basically it's a shifted rect, a shifted discrete rect, right? That is scaled by m plus 1. So now we want to compute the frequency response of this causal moving average filter. We can write it down and then try to figure out what is the frequency response. Well, we know what the frequency response of a rect, or discrete rect, right? Remember? Oh, nice. I like that, the prefix. It's very good. Yeah. A periodic sink, right? The Fourier transform of a discrete rect is a periodic sink. Okay. Now, according to the shift theorem, what happens in the frequency domain then? Kind of wrote it down. What happens in the frequency domain? According to the shift theorem. Shift in time corresponds to a modulation. Modulation in the frequency domain. Okay? Modulation in the frequency. So shift in time, modulation by a some linear phase. Okay? So by frequency. And that modulation corresponds to how much you shift. The more you shift, the more modulation you get. Because it kind of makes sense. If I modulate in one domain, basically I'm kind of modulating, shifting frequencies. That's exactly what it means. Okay? And then divided by m plus 1, and this is the usual periodic sink. Okay, so now we want to look at this. Graph it. How do we graph it? Note a complex number. How do you graph complex numbers? Come on, quick. What? Magnitude phase, that's one. Another one? Real imaginary, right? Sometimes you want to look at one, or sometimes you want to look at the other. Let's look at your suggestion. Magnitude and phase. So this is called the amplitude response of the amplitude response. This is called the phase response. This is kind of looks like a magnitude of a nice. Did you say that again? Yeah, okay. A periodic sink. A periodic sink. Remember that. All right. But look at the phase. What happened to the phase? Ignore this part. What happens here? What is this? A linear phase. Okay? The phase is linear because the phase of e to the j rho omega something is linear. That's by definition. It's a linear function. Okay? So it's a linear phase. And then weird things start happening. Right? You get to this point, And if you get to 2 pi or minus 2 pi, you would expect it to jump by 2 pi, right? But then this weird thing happens here where you have a jump by pi. And I was like, what the? Why is it jumping by pi? I mean, this is not phase wrapping. Phase wrapping is 2 pi, right? Why is it jumping by pi? Go for it. Sign change. That's right. So if you look at the periodic sink, the periodic sink should have had a sign change. And if we took a magnitude, we move that sign change, which is 180 degrees, turns out to be also pi, into the phase component. Okay? So sometimes we'd like to see that pi. Sometimes you'll see later that we're going to create functions that don't have this pi change, but then have a sign change here. Okay? So it's not going to be a magnitude thing. Okay? But we're going to see it later. But the pi shows up whenever there's a zero crossing of that function. Okay? All right, fantastic. That's great. Okay, next example. An impulse response of an ideal low-pass filter. Okay? Ideal low-pass filter. Do they exist? Ideal low-pass filter. Do they exist? Yeah. No. But ideally, they would exist. I mean, ideally, they exist, but they don't exist. Right? There's no really perfect low-pass filter. Because for a perfect low-pass filter, as it turns out, you need to have an infinite impulse response. Okay? So let's try to calculate what is the impulse response of an ideal low-pass filter. How do you calculate this? What? Inverse Fourier transform. Fantastic. I mean, you guys are so good. Okay, so the impulse response of a low-pass filter is 1 over 2 pi. You have to remember this, right, because we're using omegas. All right, integral from minus pi to pi, right, because we're integrating over one period of the DTFT, it's periodic, of this filter, or the frequency response, and then multiplying by eta plus j omega n. Okay, great. So as it turns out, this is only 1 between minus omega c and plus omega c. So we're going to just integrate this component over that period. Right? This value equals 1 there and 0 everywhere else. Stare at the screen for a second. Yep. This is 1 inside here, 0 everywhere else. So we're just going to change the integration period. And then this is 1 in that place. So we're just going to take this component. So it's just an integration of that pure frequency, of this e to the j omega n from these omegas. Okay? Well, if you try to do this, and I know you can do it, it's quite simple, in fact. It's just going to be 1 over 2 pi, which comes from here, and jn, which comes from j and n. That's the derivative of the exponent. Okay? Is that right? Yeah. And then e to the j omega n, and then, of course, you need to take the difference between the one side and the other. And if you stare at this long enough, again, you've got something plus, and then you've got something minus, right? And things like that. And when you have e to the j n with something plus and something minus, what does it comes out to be? A sinusoid. So this is really 2j sine omega c n. Okay? So e to the j something minus e to the j something minus, in the minus, is a sine. Okay? So we got this function, sine omega c over times n over pi n, which is what? What? This is not a sink. This is a sampled sink. Because it's a function of n. It's discrete. A sink is a continuous function. Okay? It is a sampled sink. Okay? Remember this. Same, but different. Because you're going to see some sampling of the sink will give you a Dirac function. You want to give me... Here's an example. Let's say I sample that sink at 0, and then I sample at this 0 crossing, and then this 0 crossing, and this 0 crossing. I'm going to get a Dirac function. Okay? A discrete Dirac function. And if I shift it by one sample, no more Dirac functions. We're going to see that effect when we're going to talk about continuous analysis of discrete time systems. Okay, you're going to see it later. Okay, but this is samples of a sink. Okay, samples of a sink. That's great. Now, okay, so let's say I want to implement this low-pass filter, this ideal low-pass filter. It's not possible. I want to do something, though, about it. Okay, so I'm going to approximate it. One way to approximate this filter is to, first of all, truncate it, because I cannot do that infinitely. So I'm going to truncate it. And then in order to make it causal, I'm going to shift it such that its center is shifted away, but the edge of it is on 0. Okay? That is going to have certain implications on the performance of that filter. Okay? It's not going to be ideal anymore. But now we have the tools to analyze what is going to be the effect. Okay? So how does it change the frequency response? So what is truncation? By the way, slides are available on the website before. You can print them if you want to. What is truncation? You chop off. What is that? If like, can you write it as a function, like mathematically?
Yeah, you can write it as a mathematical function, but you have to limit it. So you say from time
How do you limit something? What? Multiply by a window function. What kind of window? A rectangular window. In this case, because when you just crop it, right? Okay. So you multiply by this rectangular window. What is that effect on the frequency? A convolution. Really? A periodic convolution. Remember that. Periodic convolution. Same, but different. It's different. Okay, it is a periodic convolution. Okay? It's a periodic convolution of what? Of the Fourier transform of this with the Fourier transform of this. Okay? We know the Fourier transform of this. We know the Fourier transform of that. This is a rect. Right? The Fourier transform of a discrete rect is a periodic sink. So it's a convolution with a periodic sink. Okay? Periodic convolution with a periodic sink. Okay. All right. Some property in the book, 9.7, you get this periodic convolution. And so what you get really is smearing and rippling of the frequency response. Okay, when you convolve with this rect function. Now, how much smearing? Smearing is characterized by the width of the main lobe of the periodic sink. Okay? That's what causes smearing. And the ripple is caused by the side lobes, of how big the side lobes are. Okay? And so those are determined by that. Okay? And then if you shift it, what do you get then? What? A linear phase, yeah. So modulation. You get also a linear phase. The magnitude is going to be similar to the magnitude of this. But the phase response is going to be different. You're going to see it's going to have a linear phase. And the linear phase has certain nice properties we're going to talk about later towards the end of the class. Okay, moving on. Can we move on? That's great. How many people already knew all that stuff? Raise your hand. How many people did not see this before? Okay. Chapter 2, Chapter 3. Read them very carefully. All right, let's talk about the Z transform. Now, people, come up with like great transforms names like Fourier, Fresnel, like things like this. But I found a little bit frustrating that they call this the Z transform, right? I mean, Laplace, right? Laplace is actually the equivalent of the Z transform for the discrete domain. So Laplace is a continuous transform for continuous time. The Z transform is kind of its equivalent in the discrete, whereas the DTFT is the discrete version of the Fourier transform, okay, of the continuous type. But they call it Z, and the reason they call it Z is because it was invented by engineers. And it's like, it's pretty, I was like, oh, we have a Z there. Let's just call it the Z transform. I mean, it's pretty, to the point, but it doesn't have this beautiful kind of mathematical expression or name, something that, but the Z transform. Okay, so yes?
What would you call it?
I don't know. I mean, maybe the name of its inventor. I mean, it could be nice if it had a good name. If it had a good name, right? Or something French. Yeah. The discrete Laplace. Oh, that's a good one. Yeah, that's a good one. Always trust Murat. Yeah, whatever he says contradicts whatever I'm saying. Okay. So what is this used for? It's used for many things, like analysis of LTI systems, much like the DTFT. For solving difference equations, so it's the equivalent of differential equation in the continuous time. You can use it to solve difference equation. Determining system stability, very important for control. And then finding frequency response of stable systems. That's another one, another application of the Z transform. Okay, so let's go back and consider an LTI system. If you look at an LTI system with some sort of an impulse response, we already show that if you put a pure frequency is an eigenfunction of that LTI system. Okay? But what if the input is going to be z to the power of n, okay, instead of e to the j omega n, where z is a complex valued frequency, where you've got r e to the j omega n. Okay? Okay, so it's more general. Okay? I think the r should also be in the power of n. Okay? Okay. Wow, that lasted a long time. I might as well pay myself money as well. Okay.
Why is the R there?
What? Well, because the whole z is in the power of n, right? Right? Whatever, it's a constant. Doesn't matter. Yeah, forget it. All right, let's move on. You're right. You're absolutely correct. There you go. Problem solved. Okay. So let's look what the output is going to be. Okay, the output is going to be a convolution, right, with these two functions. So let's write the discrete convolution. And as you can see, again, I've got this sum over k. I've got this n. I don't like this n being in the sum. It confuses me. I'm going to take it out of the sum. I'm going to left with this. Okay, and so this kind of looks similar to the DTFT, but it's not, right? It kind of, but it's not. So instead of calling it h of e to j omega, I'm going to call it h of z. Okay? And so as it turns out, z to the power of n are also eigenfunctions of LTI systems because the output is, again, I put z to the power of n, I get some function multiplied by that. I get some value multiplied by that. Okay? And what is this? This is called the transfer function of that impulse response. Okay? And as it turns out, this transfer function exists for a larger class of h of n than h e to the j omega. H e to the j omega doesn't exist for everything, but there's even h e to z, h to the z doesn't exist for everything, but it exists for a larger class of signals. So we can analyze a larger class of them, and you're going to see some of them non-stable, or some of them stable within a certain regions. Okay. Yeah. We're going to talk about it when we talk about region of convergence. Okay. So the Z transform is defined the following way. X is Z equals to the sum with Z minus N. And as it turns out, since Z equals RE to J omega, okay, then if I evaluate Z on the unit circle, okay, if I evaluate Z on the unit circle, which is Z equal E to J omega, I get back the DTFT. Okay? Does this make sense? Okay. Now, what is a region of convergence? Okay. Regions of convergence is a set of values of Z for which that following sum converges. I mean, that's great, right? Think about it. Today you learned frequency response. What is the frequency response? It's the response of a system to a frequency. That's great. Okay. Region of convergence is the region where this converges. Okay. This perfectly makes sense. This is great. Okay. Because some things that don't make sense, but this actually makes sense. Okay. So let's look at an example. An example, I'm going to take a right-sided sequence, x of n, which is a to the power of n, u of n. What is u? Unit step. A unit step. It's 1 from 0 and on, and it's 0 for the negative values. Okay? Okay. So x of z equals to the sum of that. Where's the u of n went? Oh, I changed. Okay, so if I know that stuff is not 0 in the negative, well, I just might as well just count from n equals 0. Because I could have gone like sum from minus infinity times, of like n equal that. Okay, so this is 0 multiplied by that. So 0 plus 0 plus 0 plus 0 plus 0. It's kind of a waste of time. So let's start from n equals 0 where it's not 0. Okay. Then, inside, I got a to the power of n, z to the minus n. But wait a second, there's two n's here. I can now merge them into one. And I can just take the n out, and then az to the minus 1 to the power of n. Now I got myself a geometric series. Recall? We have an equation for this. And the equation for this beautiful geometric series is the result. So if I sum over like 1 plus x plus square and so on and so forth, I get 1 over 1 minus x. As long as x is less than 1 in amplitude. Because if it's not, it's going to not converge. Or, if you say it more efficiently, diverge. Okay? So, hence, region of convergence is only when this will only be true if z is greater or is just greater than the absolute value of a. For any other value that's inside that circle, the series will not converge. Okay? So the Z transform of that right-handed series is going to be this value as long as z is greater than the magnitude of a. Okay? The magnitude of z is greater than the magnitude of a. Does this make sense? Otherwise, you cannot write this because it will just diverge. Okay, this is not the right equation. Okay? You can maybe just write the sum, but it will never converge. Okay? So you just keep on writing it, but you cannot have a closed expression. For anywhere that z is inside, like if you want to evaluate z inside, it just blows up to infinity. Okay? All right. So that's great. Let's look at another example of region of convergence. Now I have a right-handed series with half to the power of n, and another one with minus third to the power of n. Okay, so I can do the trick that I did. Oh. Sorry. I can do this trick that I did before, and I can compute this geometric sums, and I get these equations. But those are only true if this one is true if magnitude of z is greater than half, and this is only true if the magnitude of z is greater than a third. Okay? Well, but the whole thing is only true, like this, if really z is just greater than half. Because anywhere inside here, even though this will converge, this will not converge. Okay? So I call these poles. Okay? I call these poles because for those values, function goes to infinity. Okay? I call these poles. And then the region of convergence is going to be always outside of the furthermost pole. Okay? Who has not seen this before? Oh, let's move on then. Okay, region of convergence. Okay, so the other thing I want to show is a left-handed sequence. And now I'm going to blow your mind. Out. Not inwards, outwards. Pay attention. Left-sided sequences. Check this out. This is really, really cool. X of n equals to minus a to the power of n, u of, that kind of stuff. What is this? This is a left-sided sequence, right? Because this is a step function that goes the other way. Okay, it's only true. It's only non-zero for negative values of n. Okay, all right. So now I'm going to sum from minus infinity all the way to minus 1 of this thing. But wait a second. I don't like summing from n minus infinity to minus 1. I don't like it. I'm going to change variables. I'm going to change variables to variables that sum from 1 to infinity. Why? Because it's more positive. No, but it's easier, right? Like positive is easy. Right? We think positively, human beings. All right. So if I change those, then I have to put like a minus here, effectively, and a plus here. Okay, that's all I did. Okay? Because it's switch sides. Okay, so let's stare at this long enough and say, well, it starts with a 1. I don't like this one. Let's start with a 0. Okay, we start with a 0, but then we have to compensate for the fact that we before started 1, so we have to put a 1 here. So 1 minus that is exactly like this. Okay, because I added a 1, I subtracted 1, I need to add that 1 in order to cancel it. Okay, so now this is a geometric sum as well. So now I know the equation for it. So I can actually compute it and get the following result. The following result is that this converges to 1 minus 1 over 1 minus a to minus z to the z. And then if I massage this enough, it's going to have an interesting shape. And the shape that's going to come out is, by multiplying this by this, subtracting, and so on and so forth, I get 1 over 1 minus az minus 1. But wait a second. Pattern matching, folks. It is exactly the same as the right-sided. Now I'm confused. Right? I'm confused because there's an ambiguity. A right-handed sequence has the same z-transform as a left-handed sequence. Crazy, right? Not useful. Confusing, some people might say. So what's the solution to make this, to get rid of this ambiguity? Okay, every time you show me a z-transform, if I want to know what the actual sequence that it represents, you have to tell me what is the region of convergence. Otherwise, it is ambiguous. So they have to come together. Beautiful exam question. For example, here's a z-transform, compute the inverse. Okay? Then you're like, oh yeah, I'll do this. And then most of you are going to come up with the right-handed sequences. I bet you maybe there's going to be 1 out of 1,000,000 they're going to pick up the left-handed sequence. But then all of you are going to be wrong unless you say it could be both. Okay? because you didn't define a region of convergence. Okay? Could appear. I don't know. Okay. Got 5 more minutes. Region of convergence. Expression is the same as example 1, but the region of convergence is different. It's actually inside the pole. Okay? So you've got a pole, and then you look inside. Okay? So the Z transform without a region of convergence does not uniquely define a sequence, and you have to do both. Okay, let's look at another example. This is an example of a left-handed sequence and a right-handed sequence. Okay? So you can compute the same thing as example 2 and get exact same result, only this one has a region of convergence less than half. This one is greater than a third. As it turns out that the region of convergence of the entire sequence is between in between those regions. It's a ring. Okay, that's the region where you can write that function. Otherwise, you cannot write it. It's going to explode. Okay, so that's the region that you can write it. Okay, here's another one. Same thing, only we flip. This one is a right-handed sequence. This is a left-handed sequence. That's great. I can try to do the same thing, but the problem is that this will converge for z equals z greater than a half. This is converge for z less than a third. Turns out they'll never converge. So the region of convergence is empty, okay, or 0. Okay, the 0 set. What about the region of convergence of the sequence a to the n? This is a two-sided sequence, where a is not equal 0, because then it's a 0. Doesn't make any sense. As it turns out, this two-sided sequence doesn't converge as well. Okay, so bummer. And the reason it doesn't converge is because on the negative side it goes to infinity. It depends. Right? Depends what a is. But if a is less than 1, then the negative side is going to go to infinity. If the a is bigger than 1, then the positive side is going to go to infinity. Okay, so.
Isn't it real that if we have an eigenfunction, then x is the eigenvalues, get different eigenvalues depending on the region?
Yep. Yeah, because the system just doesn't, you can't evaluate that. Right? So the system really only is stable for those. You can't really put anything in the system. Everything's going to explode, right? Outside. Okay. It doesn't explode for z's that are inside the region of convergence. Okay, so let's look at a different one. Let's look at a finite sequence. Okay? One of them is this is a finite sequence. A to the power of n, u of n. And the question is, what's the region of convergence? So what's its z transform? And the answer is that first of all, it's finite. And if it's finite, it's always going to converge. Okay? Remember that. Something finite going to converge because it's finite. It doesn't go to infinity because it converges. Unless you put infinity in that sequence, and of course that doesn't make sense. Okay? So when you sum from 0 to m minus 1 of this thing, it's finite, always converges. You can use this equation to evaluate what it is. There is a pole over here, right? There is a pole. And you're just like, wait a second, there's a pole, but there's also a 0 here that will cancel that pole. So if you decompose this, you break it into its roots, you'll see that there's exact 0 that be on top of this pole and we'll cancel it. And so you've got yourself basically just zeros, okay, of this function. So for certain z's, this will have zeros in it. Okay? So it always converges for z that's greater than 0. And if you look at what it is, if I have an infinite sequence, has a pole over here, region of convergence outside. If I crop that sequence at 100, then the z transform, not going to have a pole anymore, except in the center, which is fine. Okay, so you cannot have a z equals 0 there. But everywhere else, it will converge, and it will have 99 zeros that are going to be distributed along the, kind of the same radius. And there should have been a pole here, but it would just canceled with a 0. Okay? So it's kind of interesting. Right? This kind of so what is the pole from the Z transform? Is like, you know why it's called a pole? You think of it as like a canvas, tent canvas, and then you take a pole and you stick it up to infinity exactly at those points, and then you look at what the function is. Right? This is basically what it means. Okay? And when you put a 0, it means that you take a peg and it in the ground, and you nail it to 0. And so everything here is nailed to 0, and here is 99 times infinity, pushes things up, this pegs it down, and so here it's going to go a little bit up. And that upness is going to leak to the unit circle, which is going to mean something about what that filter is going to do. Okay. The unit circle is the evaluation of the Z transform. Okay, I ran out of time. There's actually not that many slides left. One of them is properties of the rock for different type of sequences, and so on and so forth. Some properties of the Z transform, and how you compute an inverse of the Z transform. And one of the most useful way of compute it is to decompose it into this fractions. And so the reason that's useful is because transfer functions that look like that can be represented as an autoregressive moving average model, which is easy to implement. Okay? So I'm not going to go over this next time. I've caught up, go over those, read chapter 3, and I'll see you, most of you, tonight. Okay?